Alright, so special integrating factors. So this combines two sections into one. Um, the first part we talked about is how do we solve for differential equations when we have a different situation and we had to multiply by an integrating factor to make it work. This is also going to be applied when we have dy dx's implied for the last section when we came to exact equations. Okay, so what we're going to do is again combine them itself, and more importantly, we're going to learn actually how to find an integrating factor in general. So we can use this for any type of situation, not just this one particular now. So let's go for first definition. If we're given the equation, it is not exact, meaning remember these partial derivatives do not equal to one another. Therefore, if we multiply it by an integrating factor, the entire equation basically just multiply by some u function to m and n, and now becomes exact. Okay, so that's the nice thing is, well, again, the question is, well, how do we find it? But first, let's just see how this would actually work. Okay. All right, so we have this equation, and we already given that the integrating factor is x y squared. Okay, so the first thing we do is multiply x y squared to both these two here, or just multiply the entire equation by it. So this ends up being 2x y to the third minus 6x squared y squared dx plus 3x squared y squared minus 4x to the third, and just regular y because of the inverse cancel, the negative power cancels. So this is the actual equation we're dealing with. And now, believe it or not, it actually works out. So if we take the partial derivatives of m and n, so if this is m, partial with respect to y gives you 6x y squared minus 12x squared y. And if we do the same thing for the n value, but with respect to x, we get 6xy squared minus 12x squared y, which you get exactly the same situation, which is kind of interesting, huh? Okay. All right, so now that we verify that it actually does work, and this is actually an integrating factor, so now let's actually solve for it. Now at this step, so we do the same thing as just solving for a exact equation. So we take the integral of m and n respectively. So integrating with respect to x this time gives you x squared y to the third minus 2x to the third y squared plus that. So this is our f function. And if I do the same process for n, but now taking in respect to y this time, let's see, we get x squared y to the third minus 2x to the third y squared. And there we go. Okay, so we have this in common. We also have that in common. So it looks like there is no function of just x and function of just y. It's just those two put together. So our solution is c equals x squared y to the third minus 2x to the third y squared. Okay. So now the whole process becomes, well, how do we solve, or how do we find an integrating factor? That's the key thing. We have to figure out now how we're going to do. Okay. So for that, we're going to go back to our basics. All right, so we know if it's exact, this is true. Okay. And we're going to tweak it. So we're going to multiply both sides by our integrating factor of u. Okay. And now we're going to just take the derivative. But again, this is a partial derivative because u could be represented as x, a function of just with both x and y into it. So doing implicit differentiation on both sides gives us this background here. Okay, so at this process, we would basically just want to manipulate some stuff around till we get something like this. Okay. Now, all I really want to do is solve for, or in other words, just find a way that can simplify and just use on one side. That's the key thing. So if I just really want to solve for this process, and I eventually get this. So after a lot of work and doing a separation of variables, I get this. Now, we already know this. This is going to, if you take the integral of both sides, this is just 1 over u, which is going to be natural log. Okay. And since I want to solve for u, I take e to that power. Those cancel, and I just get u. So really, we get the actual theorem here. So if this is true, so if we get the partial derivative with respect to y and the partial derivative with respect to x divided by n, meaning this exact process here. But if this is completely in terms of just the variable x, no y at all, therefore our integrating factor is the e raised to the integral of all of this. Because again, right, we're taking the integral to both sides. So if this is one process and we just raise it to the e power, we get exactly that. However, if I flip it, so flip these around and divide by m instead, and if that is just in terms of y, then this is going to be our integrating factor. About the same process, the only difference is what we subtract by and what we divide by. Okay? So if it's easy to remember, it's m and then you divide by n, and you divide by m. You want to follow like the first term rules there. Okay? All right, so this is our major theorem of this section, is how do we actually find an integrating factor? So this goes back to a couple sections where we can actually do it and solve for it individually. Okay, so let's see how this would actually apply. All right, so let me put this aside because I'm going to need this definition in a little bit. Okay, so let's first check that it actually doesn't work. So this is m, this is n. So the derivative of m with respect to y is just going to be 1. The derivative with respect to x with this n is just going to be 2xy minus 1. So right after that, you notice they don't equal each other, right? So therefore, it is not exact. Okay, so now we got to find our integrating factor. So again, just going back to the process, we got to check which one actually works, because one or the other will actually work itself. Okay, so why don't we just try the first one? So the first one is I just subtract m minus n. So in other words, that minus that. Okay, so let's see. So we do 1 minus this derivative all over, in this case, n. So the original n value. All right, so let's see what happens here. We just get negative 2xy plus 2 all over this. Okay, so we've got to be a little bit deceptive, right? Little portion is, well, I could factor some stuff out, right? The top I could factor a 2 out, so that's what I'll do. Actually, I'll factor out a negative 2. And on the bottom, I'll factor out a y, or sorry, an x. And notice these actually go away. And look at that. This is in terms of just x, which is exactly what I want. So therefore, this is going to be my integrating factor. So my integrating factor, just u of x, is equal to e raised to the integral of, let's put this on the outside, negative 2 of 1 over x dx. All right, so integrating this is going to be natural log. And again, I really don't like this, so I'm going to try to simplify as best I can. So going back to properties of natural log and log means I could bring it to the power itself. And now e's and natural logs cancel, so our integrating factor is just going to be x to the negative 2 power. Alright, so we're actually almost done now. Now we're going to follow the process we did in the last example. So namely, doing exactly this. Alright, so multiplying and then taking just the integral of both situations. Okay. Alright, so let's just multiply this part. So it's the integral of this by m first. So if I multiply it, it's just going to be 2 because the x's cancel. And this stays itself with the y there. So integrating with respect to x, it's going to be a negative. Okay. So that's one side. And now I do the same thing for the other side. So now multiplying this by x to negative 2 power, the x's cancel. And now these ones end up being x to the negative 1 power. All right, take an integral. Oh, with respect to y, that's right. There you go. All right, so now that we have those portions, let's see what they have in common. So it looks like just that. And everything else they don't. So we have there we go. And again, if you want, you can put c equals all that. Well, it's implied, right? That's going to be our f of x function, fxy function. Okay. All right, so let's keep going. Let's try some more and see from there. So we have another situation. So I'll leave it to you guys to verify that actually, well, we need them anyway, so I guess we could just quickly do this. So taking it with respect to y gives you 4y x minus 1. Take the with respect to x is just going to be 1. So again, doesn't work. Right? Okay, so now we got to check. So what can we do? What can we do? Well, I want to try them the other way. Since this one worked that way, hopefully this one works the other way. So let's try this situation here. Since this one worked the other way, maybe just flip it around so you can see how it's going to work the other way. So it's going to be, in this case, this value minus that value. All over m. Right, so simplifying this a little bit. We get that. And notice we might do the same thing we did last time, so we're going to have to factor some stuff out. So let's factor out a negative 2 again. So this becomes positive 2xy minus 1. Let's factor out a y. Oh, there's an x there. There you go. And these cancel again. So we get, oh, actually, let's check. So in terms of y, and that's exactly what we want in terms of y, so we got to check. So now our u of x, our integrating factor, is going to be e to the negative 2 1 over y, or integral 1 over y dy, which if you notice is the exact copy of what we just did above, just in terms of x instead. So I'll just skip that step and say u of x is going to equal to just y to the negative 2 power. So just change the variables there. Okay. Alright, so now that we have our integrating factor, so we multiply and just follow the steps we just did above. So integrate with, so multiply this out, so this times our m value, so y's will cancel, we just get 2x, and this becomes negative 1 power dx. So in respect to x gives me x squared minus y to the negative 1x. And now doing the same thing for the other side. So that's nice, it's just going to be y to negative 2x. Right, so integrating respect to y, so add 1, so be negative y to the negative 1 power x plus the g of x function. Alright, so that's what they have in common. So our function is going to be exactly that, plus this, and it looks like that's it. There we go. Alright, last step of situation down here. Alright, so with respect to y will just give me 4. This will give me 1. Alright, so that's not bad. So it looks like really doesn't matter which one you try. Well, let's see how it fails. You can see, understand, like it's going to be one or the other. Let's just say. So why don't we do the first one? So we subtract m minus n and divide by, or actually, let's do the one we just did, so you can see. So we'll do n minus m and then divide by m. So n minus m divided by m. Okay, so this is what we get. As you notice, there's no way this is in terms of just y. Right, so it doesn't work out. So that's how you know it's going to be just one or the other. So we just go back up here and retry it. So that didn't work. So we'll do the other way. So we'll do 4 minus 1 over n, which is just x, which just gives you 3 over x, which is perfect because that is in terms of just x. So kind of get the pattern. And I'm sure you can follow the pattern from there. So u of x is just going to be x to the third. Nice thing is, you know, finding the integrating factor in u is about the same process. If the e's don't cancel, usually something's off. Most of the time, there's going to be a lot of natural logs that cancel things out, and you just get, you know, a function that's kind of nice to multiply by. Okay. All right, so we have our u of x. So we multiply and integrate. So this times that part's going to be x to the 5th. Okay. All right, so there's my f. And on the other side, that's going to be x to the 4th. So if you notice, all you do is follow the process and just remember what actually you're integrating. In the situation-wise, for example here, we're integrating with respect to y, so not x, means it's just going to be a constant. That's pretty much it for that side. So we have that, and that's left over. And there we go.